So our next speaker, I guess Naveed is the kind of person who we should say needs no introduction, but my job is to introduce him. He is, of course, the executive director of AIT Consulting. He's an AIT alumnus, and before coming to AIT, he graduated in civil engineering from the University of Engineering and Technology in Lahore. So he's a Pakistani native. And Naveed's expertise is of course, in structural engineering. He specializes in structural system development and evaluation, in performance-based design of structures, computational mechanics, modeling, analysis, and design of bridges, particularly, and tall buildings and special structures. And Naveed is going to be speaking for the next 25 minutes or so on the topic of designing and constructing buildings for higher performance, cost effectiveness, and sustainability. An overview. Naveed, please.
Thank you very much, ladies and gentlemen, and thank you so much, Kunshawalit, for setting the right stage for the discussions to follow in this day and also tomorrow. And many of the things that Kunshawalit has identified, we will be also discussing those in a little bit more detail in our presentations today. This one, as the title suggests, is more of an overview of the issues, I would say, in terms of the tall buildings and what is happening around the world, and how the performance and cost are related, and how the performance can be increased, or the cost can be reduced, and also more about the definition of cost and other factors that affect the development of the tall buildings, and not only tall buildings. This applies to most of the structures. We choose the tall buildings, as one of my colleagues suggested, to attract more people, but basically what we are going to discuss applies to all types of buildings. So just briefly, because the time is a little bit tight, I will skip some of the slides that actually Kunshawalit has already highlighted, the need for the tall building. And if you quickly go through the world maps at this time, for example, the percentage of the urbanized world, we can see where the urbanization has already taken place and where it is going to take place. And the lighter color is where it is going to take place. And the darker color, of course, is where it has already taken place. This is where the rate of urbanization is now going. And you can see that there are hotspots, of course, in Africa, some countries, but also our region is still going to go through a very fast rate of urbanization in the coming years. This slide is quite interesting and also a bit alarming, and at the same time may present us with the opportunities that we are looking for the tall buildings. If you see here, you can see that most of the growth in the population in the coming years is going to be in the urban area. So the rural, even though the population is going to grow, mostly it's going to grow in the urban area. So that means the urban population percentage is going to go substantially, which means that we are going to be building a lot of housing, a lot of buildings to accommodate this urbanization. This is how the urbanization trend is likely to follow. This is projected to follow each year, starting from the year 2005 until the 2030. And you can see gradually the shifting of the color, and all of the countries, especially the region that we are living in, becoming more and more urbanized. So when we look at these things, it is quite obvious that we are going to be needing a lot of construction of building for housing for all these people who will move into very tight spots. That means land values which are very high. The scarcity of land will be there. So obviously we are going to find solutions for this huge demand. If you look at the number of people moving in until 2030, it runs into billions. And somebody mentioned that millions of people are moving every day from the villages to the cities, and they're going to be need for them to be accommodated. So if you look at the comparison, very rough comparison, this is not meant to be an accurate representation, but very, very rough comparison between land use. So you can see that where you normally would have about 10 houses or 10 families living, with a tall building, you could have up to 200 or 300 or 150. living in the same spot. So if the urbanization needs are high and the land is going to be scarce, and also we need to be closer to the workplaces and so on, then obviously the option will be to build taller and higher. And tall buildings, that definitely is going to be one of the main need of the future in the cities, and something that we cannot turn away. In fact, I would like to talk to you about the case of London a little bit. I was there a couple of weeks ago to attend the conference on the Council on Tall Building and Urban Habitat, CTUFB, and it was very interesting to see the two cities, London and Paris, how they have resisted the tall buildings for a very long time, and how much difficult it is to build buildings over there. And now a few buildings have been approved, and now they're building very nice, interesting buildings. And just one of them, for example, the Shard, which is the tallest building in the Western Europe, which is actually not that tall comparing to what we build in Asia. It's only 75 stories high. So if you compare to buildings in China, in Dubai, or even in Bangkok or Manila, buildings would be higher than that. So this is currently the tallest building in the Western Europe. And it took them 10 years from the conception to building because of the approvals, and they have to go through hearings and public hearings and criticism and so on. And finally, they are able to build this building. And I had the opportunity to go on top of this building and look at the view of the city from there, and it's obviously very interesting. In contrast, if you look at another building which is coming up in China, which is going to be the tallest building, even taller than the other ones that had already been constructed, they plan to do it in 7 months. So you can compare the building, which is going to be very tall, almost 200 floors high, and it is going to be built, and they claim, and it's going to be built in 7 months, not 7 years, 7 months. And that is, and the owner of this building and the developer was also there in London, and he presented this building and how they're going to do it. And they have actually already proved that they can make a building, 30-story building, in 15 days, complete from beginning to the end. And that has become quite a sensation on the internet. If you go to YouTube, you can see the video about the construction of those buildings. They call I think, T30 buildings, that they build it, 30-story buildings in 15 days. So we can see that the technological developments that will be needed to build buildings so high, so fast, are going to be totally phenomenal. Nothing what we have seen before. But at the same time, we cannot forget and neglect a lot of other needs that, as has been pointed out in the development, is going to be a lot of need for other people who will not be able to afford or live in this area, to also develop housing systems for them. And we have a presentation in the afternoon just talking about social and affordable housing. So coming to the components of a building, because now we are going to talk about what the building can, how we can sort of build a building with the high performance and lower cost and so on. So let's look at the systems first. Before I go any further, we need to know that building is not structural engineers' domain entirely. There are so many other professionals and systems involved. And two main important systems, one is of course the structural system, which houses every other system, and the second one is the vertical transport system, which is the elevators. So if you go to a world conferences on tall buildings, you will find two people mostly there, the structural engineers and the elevator build people, because they are the ones who are developing the technologies very fast. In fact, the recent awards that were awarded for innovation, one of the award went to the elevator company for tall buildings. And the reason is that they have developed this new carbon fiber, which can build elevators which are much faster and much taller. But that will affect the structural engineers, because if they built elevators which are faster, they're going to need fewer elevator cores, which means lesser structural system left for us to use. So development in one technology may actually be not so good for the other discipline. So anyways, because this is an interrelated, interdisciplinary project, so everybody has to work together on a building system. But of course, the structural system being the core, the skeleton where everybody else will put their system on, is critical. Of course, just as we have many systems, we also have many members of the team in a tall building, and we respectfully agree that the architect would be most likely the team leader, unlike the bridges where the structural engineers could take the lead, and then structural engineers and everybody else will work together. And it's a huge coordination problem between all these disciplines. And Singapore is one of the countries which has completely automated this coordination, because everybody shares the same set of drawings, same set of plans, so that there's a less chance of error or miscommunication between various disciplines. If you look at the building systems, actually this is more like the conventional range that has been developed over the years, and people have been working on these systems which go as high as 110 floors. But now we are talking about buildings which go much higher, 200 floors, or even some buildings are planned to be higher. So that means these conventional systems will need to be re-innovated or redeveloped. And we have seen the tubular systems, we have seen the core wall systems, and so on. And now there are variations of these systems which are now leading to taller and taller buildings. If you look at the story range, the tall building range finishes at about 110 stories, and then we start with the ultra tall range. An ultra tall range is now extending its boundaries up to 200 or 250 floors, or even higher, and that's a totally specialized and a different era. So not everyone of us may have a chance to work on an ultra tall building, but we will see more of them being built, especially. And in fact, if you look at the development in the last 10-15 years in tall buildings, almost all of the tall and super tall buildings have been built in Asian countries, mostly in China and in the Middle East, and some now coming in this region also. So we can see clearly that the market for, or the field of structural engineering is now going to another era, which is the super tall buildings, and that is going to need higher technologies, newer systems, and newer techniques. This is just a snapshot of some of the buildings, and this is quite common. You can see it on the internet everywhere, but you can see how the Eiffel Tower, which used to be the tallest structure on Earth at some time, now is dwarfed by all of these tall buildings which are coming up, and super tall buildings which are coming up. And every building tries to be taller than the previous one. And then this trend seems to be exponential, not linear. So now, since the 1950s and so on, or 70s, the trend to build faster taller has actually accelerated. So now we see that the buildings are becoming taller at a much faster rate. And this is all thanks to the developments in the transportation system, in the computing systems, and so on, some of which we will talk about. The other system which is coming up now, which is becoming quite popular, in addition to the conventional system, is the diagrade system. And this is being used, it has been exploited quite heavily in Dubai, buildings in Middle East, and also many new buildings in England and Europe are using this system. In fact, one of the presentation in London made by one of the senior engineer was comparing that whether these diagrade buildings would be suitable for seismic zones or not. And it was a conclusion that they may not be, because of a very large stiffness that they carry and low ductility that they may have. So one solution which may work in a low seismic zone may not work in a high seismic zone. So diagrade systems, or maybe some modification of that, will be developed, which will be adapted to the seismic zones in the future. And one of that development is the BRB, or the buckling restraint brace system, which can replace the diagonals in the diagrade, or place these strategically so that they will absorb the energy, or they will provide the required ductility in the system, which is otherwise inherently very stiff and brittle because of the buckling of the diagonals. And this use of these BRBs has also now in Asia also it is becoming popular. We had the opportunity to work on one tall building in Manila. In fact, the designer of this building is also one of our audience, and he will be one of the panelists also in the afternoon session. And we also use this, some research is being done in AIT on the effective use of BRB, not only for tall buildings, but even for smaller buildings, 4 or 5 story high buildings, for retrofitting and improvement of seismic performance. This is the building that I mentioned, which is in Manila, and it's now is completed. Some other building awards. These are, I just take these pictures from the awards given by the Council of Tall Buildings and Urban Habitat in the various years, starting from 2012, 2011, 2010. So this is the buildings that they awarded as the top innovative buildings of that year. So just to give you an idea what the developments are going on in the building designs. Now we can see that there are so many structural systems to choose from or to develop. The question is, how do we select a system? How do we weigh the choices between a system? How do we say which system will be better than the other for an application? And of course, for that, many formal and informal methodologies are available. Some of them are, most of them have to be multi and interdisciplinary in process because many professionals are involved. So we cannot optimize or select the system only based on one criteria. We have to keep all the other criteria in mind too. So things like fuzzy logic, expert systems, value engineering, blackboard approach, rich pictures, and analytical hierarchy process, they have been all used to help in the selection of the system in a more formal way. Of these two, I will just briefly mention the two of them in which AIT also has been doing some research and has done some work in the past on some projects. One of them is AHP, the analytical hierarchy process, which can be used as a tool to make choices or compare systems and select the systems with the appropriate value. Second one is the rich picture diagram. This is actually by one of our students. She's also an architect and also designed this room layout for you. So she has done some work and prepared some rich picture concept for the total system interaction between various parts of various disciplines, various systems, and so on. So these concepts, which go a little bit more than our conventional structural engineering, those will be useful for helping us to choose the systems. Let me now come to the important aspect of cost and performance. First of course, the one question would be, what cost are we looking at? Because cost can be defined in a many number of ways. Then we also have to see what factors affect the cost. How to reduce the cost is the key, obviously. But at the same time, the relationship between cost and performance. Is it that we reduce the performance? If we reduce the cost, the performance will go down, or is it that we increase the performance and the cost will go up? So these are the basic questions that obviously we can address. The cost can have many components depending upon who is looking at the cost. It could be financial cost for borrowing the money from the bank, and the planning and design cost, starting construction cost, and so on and so forth. I don't want to go into the details of each one, but we know even if you look at the emotional cost, and I may say a few words about the emotional cost. There has been a study by the psychiatrists that the people who drive through an urban environment which is ugly or not good to look at, they get depressed by the time they reach the office, and they perform less than the people who don't have to drive through those places. So there's a direct correlation between the people's output, emotions, and their getting angry or not getting angry, depending upon whether they drove through a nice place with the nice buildings, nice bridges, or not so. So that also has an impact on the cost of the total. So cost, broadly, we may say that cost is actually the consumption of particular resources at a particular time. So we may say that's the cost of that thing at that time. And sustainability may be a broader term which may include all of the costs at all of the time. And obviously, we will look into sustainability aspects later. Also today in the afternoon, we have a very interesting presentation about the sustainability and what makes building green or otherwise in the afternoon. So basically, one of the things is we should build to last. The buildings should be longer life so that the consumption of resources can be reduced over the life cycle or over the several life cycles of the buildings. So I will leave this to the afternoon session. Another one that also is needed is once we construct the facility, how do you monitor the performance of the buildings or the facilities in terms of the cost, in terms of the energy use, in terms of the resource use, in terms of the need for their repairs, in terms of everything. So the monitoring, evaluation, and managing of the built facilities is just as important as designing the facilities or building them in the first place. And again, we have a presentation to address this particular topic in the afternoon. Now, let me come back to the question of the cost and performance. And there could be three ways that we can look at cost and performance. The first one is the easy one. That means you want a higher cost, you spend more. That is the general feeling. It may or may not be true, but it seems to be true that, okay, if you want higher performance, you spend more. Second could be that we want to increase the performance at the same cost. Or third could be that we want to get the same performance for a lower cost. So the real challenge is on the second two parts, which is to either increase the performance for the same cost or reduce the cost for the same performance. So what do we need now? First of all, we need a measure of performance so that we can see what is performance that we are measuring. Second, we need a measure to evaluate the cost effectiveness or the cost. So when we have these two measures, then we can move ahead and then do this development. So the enhancement of the performance from the structural point of view, I'm not talking about other performances right now, could be dynamic response, lateral load response, and irregularity, and so on and so forth, and many explicit parameters. Cost effectiveness could be capacity utilization ratio, reinforcement ratio, concrete strength, rebar quantity, in any number of ways that we want to define. So both the performance and the cost can be defined in a number of ways that we want to compare. Obviously, one term that we all want to do, we have all heard, is optimization. And this is something that actually is very, very hard to do. In fact, impossible to achieve in a given system. And the reason I will explain to you in a while. Because the optimization can be done at many levels. It could be a micro level of optimization, or it could be a system optimization, or the whole, or the component optimization, and so on. When we talk about optimization, even if we have to optimize one thing, it might produce unoptimized results for the other. So, for example, a good solution for structure may not be a good solution for environment. So the total optimization of that will be lost when we compare the overall system, which is combining structure and the environment. I will give you a very simple example quickly to make this point valid. I just look at a small building. It's a 15-story, 20-story building. And we look at the design of the column for that building. And if you forget about earthquake, forget about everything, just the gravity loads, the change will be something like this. So we can see that there will be an increase in the load as we go down. Everybody knows that. So if you want to optimize, if you want to design a column which is completely optimized at every floor level, then you will need a column size which may be different at every floor level, reinforcement ratio which will be different at each floor level, or the concrete strength which is different, and so on. So no two floors will have the same design. Is that optimized? Of course, you can say that I have optimized one column for that loading, but the entire column is not optimized because people have to change the formwork, people have to change their reinforcement cage, and many times it is not even practical to provide exactly what you want. So a local optimization of one column will definitely produce an unoptimized solution for the entire column. And if you compare many columns, then they all cannot be different. Many of them have to be the same. So which means that we cannot produce an optimized solution for a building purely on the local optimization. Also, there are so many choices for the column section that it is unbelievable how many things you could do to carry that load. And obviously, we will almost never end up with the column design. The building will be completed before we finish the column design. The other kind of factor or a measure could be the utilization ratio. Utilization ratio basically can compare what is required against what is provided, and we can set a range that, okay, this is an acceptable range, and most of our structure should be in that range. Some can be outside the range, and so we look at the overall cost economy in terms of the distribution of the utilization ratio in the structure. For example, in this particular case, the very good one is the 0.7 to 1. That means we have designed for about 70 to 100% efficiency. If you design for less than that, that means it is uneconomical. If you design for more than that, that means it's unsafe. So we have to be somewhere in that range of 0.7 to whatever range we define, and then try to bring most of the structure in that range. Practically impossible to have all the structure there. But the target should be that most of our utilization of the resources or the material should be in the range that is economically feasible. So these measures can help us to after we finish the design, we can evaluate the utilization ratios and see whether our structure is cost effective or not. And then if not, then we can try to change the design to bring it in this range. Another second side of the coin is that how can we improve the performance and not the cost. Now, this is a very simple example again. I'm just giving very, very basic examples. This is the reinforcement in a shear wall. And on the right-hand side is the you can say one performance measure of the wall, which is the moment and the axial load capacity. And the line here, that is the original design, basic design with uniform reinforcement like this one. We could achieve more higher performance by simply redistributing the reinforcement in a more efficient manner so that the cost is not increased, but the performance is increased. Or if we want the same performance, we can take out a few bars from this wall and then reduce the cost while getting the same performance by rearrangement of the reinforcement. So these are extremely trivial and basic examples, but they provide us the I would say direction that there are opportunities for performance enhancement and cost reduction within the system by innovative thinking, by looking at the things critically and finding solutions. Cost and time, they are related. Time is money. Everybody says that, and in construction it really is. If you finish too late, you cannot collect the rent too early, and so on and so forth. So we have to balance the cost and time in a very, very difficult way, because sometimes if you want to reduce the cost, you have to spend more time. And if you want to finish something quickly, you have to spend more money. So there's a balance between cost and time, which are both, in a way, money or the cost. So that's a challenge that we also have to consider. And there are techniques that can reduce the time without increasing the cost. I will just show some of them later. Let me just, how much time do we have? Oh, okay. Right, so I'm way slow. Okay, I'm way slow then. You should have given me a warning, John. Okay, so very quickly, let me just say that I have to then quickly go through this one. We want to see what is the responsibility of a building, who has the responsibility of the performance of the building ultimately, and these are the people who are involved in a building. So if something goes wrong, who is responsible? We can't really point the finger. But if you look at very old code, and I will not spend too much time after this one, it was written that if the building is not constructed properly, which is the implicit specification, and it falls down and kills a person, which is a performance criteria, the builder should be put to death. We are lucky that we don't have those direct laws as strict as that right away. But this is a clear indication of the specifications of the performance and the consequence. And this is where our industry is leading in terms of there are other, I will skip and go right to this slide. So basically now we are talking about the performance-based design in which the client, the designers, the independent designers, the guidelines, they all come together and they decide what to expect, how to achieve it, and that requires knowledge, skills, and tools, which is actually technology. So to do this, we need to have the knowledge, the understanding of the knowledge, the skills to apply the knowledge, tools that we know how to use, and rightly apply those tools to achieve the performance. And now the performance design is also going through another evolution. The first stage was that we have just the limit states of the performance, immediate occupancy and so on. The next one is also talking about the replacement value, the dollar value, the casualty rate, the downtime in days, how longer will it take to repair. So all those things are also becoming part of the performance evaluation. In fact, it's going to the next step. And these are some of the guidelines that are used. And Dr. Penning will talk about that in the afternoon, about the earthquake and wind impact on the performance. And Dr. Napanon will talk about the foundations in that context. So we will have 2 more presentations on this one. The last one that I would just like to emphasize is that now the next stage is the consequence-based engineering. That means we cannot simply say, in the past, we used to say, I follow the code, so it should work. But I don't know the performance. Now we have to find the performance. And we say performance is good or bad. But what if the performance is actually not achieved during an event? What is the consequence? So we also need to now look at the consequence. And then that requires a much interrelated and interdisciplinary approach to the whole problem. And also, again, we have some presentation about the risk and so on in the afternoon. So I think I've completely run out of time. I have some more things to talk about. Maybe if we have time, we can present it another way. Thank you so much, John.